Intel software solutions for diverse computing architectures. And in particular, we'll be looking at the Intel oneAPI Math Kernel Library available in beta form. So today, each kind of data-centric hardware typically needs to be programmed using different languages and libraries, which requires different code bases. In addition, there's different tools for supporting the platforms. So that means developers have to waste time learning different sets of tools for the different platforms. And even within one platform, there can be different tools depending on vendors within it. And so the different kinds of data-centric hardware include CPUs, GPUs, FPGAs, and other accelerators. So this means every time we want to develop software for a different hardware, it requires a separate investment in time and effort. And there's not a lot of ability to reuse the previous work to target a different architecture. So those are some of the challenges with the way the ecosystem is today. So that's what motivates a oneAPI programming that supports a diverse set of data-centric hardware with common programming language or APIs and consistent tool support across platforms, allowing for a shared software investment across the diverse data-centric hardware. So Intel's oneAPI is a project to deliver unified software development environment across CPU and accelerator architectures. It includes a unified language and libraries that deliver full native code performance across a range of hardware, as you can see at the bottom on the right, including CPUs, GPUs, FPGAs, and AI accelerators. So as you kind of work your way up the diagram on the right, we have oneAPI as the foundational programming stack, and it's used to optimize middleware and frameworks that sit on top of it. Those frameworks can include TensorFlow and other artificial intelligence frameworks. And then on top of that is the optimized user and industry applications that can take advantage of the middleware and frameworks or the language and libraries that sit at the bottom. And then all along the side, we have the oneAPI tools, including profilers and debuggers to allow profiling and code optimization. And so we have this common developer experience across all the different architectures, CPUs, GPUs, AIs, and FPGAs, allowing for unified and simplified language and for expressing parallelism and achieving native high-level language performance. And one of the other key aspects of it is based on key industry standards and open APIs. So there can be cross-vendor implementations. And so looking at one of the libraries in particular, the Intel oneAPI Math Kernel Library available in beta form. If you're familiar with the Intel Math Kernel Library, today you'll know it has C and Fortran APIs for a variety of domains, including dense and sparse linear algebra, fast Fourier transforms, vector math, vector RNGs, and more. So in addition to the C and Fortran support on CPUs, the oneAPI Math Kernel Library includes support for Intel Processor Graphics Gen 9 on a select set of domains and functionality. And does that via data parallel C++ language support. So compared to the C and Fortran functions, the oneMKL data parallel C++ routines use C++ standard types for complex numbers and integers. They take an extra argument, a Q, specifying where the computation should occur. We have two different types of data parallel C++ APIs. One is a buffer-based, and one is a pointer-based or unified shared memory USM. So the buffer-based data parallel C++ APIs use a one-dimensional DP C++ buffer to store vector and matrix inputs, And then for functions that have a return value, there's an extra buffer or a pointer in the case of USM APIs for those functions to pass the return value. And the USM-based APIs return an event to specify when the computation is completed. And they can also take an optional last argument of a list of events to wait for before starting the computations. And data parallel C++ handles the memory transfer. The user should ensure the memory is on the appropriate device for the best performance. So we can take a look in a little more detail at the different domains and their support for the Intel processor graphics Gen 9. So you can see that everything in a white box has C and Fortran support on CPUs. So that's same as what is in Intel Math Kernel Library. But then in the Intel oneMKL beta, the items in red denote that there's support on the Intel processor graphics Gen 9. The solid red line around BLAS and vector math indicates that there's full support for those domains on the Gen 9, and then the dashed red lines indicate that there is partial support. So LAPAC, ScalaPAC, multidimensional FFTs, and vector random number generators all have some support on the Gen 9. And so looking in kind of even a little more detail, the oneMKL beta was publicly released last November. It's also referred to as Beta 3, and then the first update, the first public update to it was released just this week, also known as Beta 4. So what's in there is the support for Intel processor graphics Gen 9, the GPU, and then support for the data parallel C++ language bindings for the different domains. So BLAS supports fully on CPU and GPU with both buffer-based and the pointer-based or unified shared memory, USM, interfaces. Vector math also supports that full array. LAPAC has select support for buffer-based interfaces and just initial USM support. Sparse BLAS has buffer-based interfaces, as does some functionality on the FFTs. And then RNGs has both buffer and USM-based interfaces for select functionality. We also know, though, that it may not be possible to change your application to use DPC++ interfaces, and you may want to still take advantage of Intel GPUs. And so that's why we have support for OpenMP variant of Offload, currently for C and C++, onto the Intel processor graphics Gen 9. And for BLAS, we have full support for all of BLAS and C BLAS, as well as the BLAS-like extension called GEMM. LAPAC has support for LU factorization. FFT has one-dimensional complex to complex. And as in the future, the amount of functionality and features supported will continue to grow. This is just kind of a snapshot of what is currently available today. So now that you kind of have seen what there is, let's take a look at an example. So we'll start first with C APIs, dense matrix multiplication for double precision, GEMM. So hopefully this is fairly familiar looking. So we include the mkl.h header file, and then we have a number of sizes and other parameters, alpha, beta. So you'll notice the sizes are mkl int in the C example. We allocate matrices using mkl malloc so we can align them for better performance. We initialize them somehow, and then we compute C equals A times B on the CPU using the cblas dgem function. And so if we want to now change that to use the buffer-based data parallel C++ APIs. You can see there's a number of changes that have to be made, but not everything changes. So the changes are in blue. So you can see now we have a specific header that we use for the oneMKL data parallel C++ APIs. And instead of MKL int, we now have oneMKL, or we use standard types for the data parallel C++ APIs. And then one other big difference is we now specify on which device we want the computation to run. It can be host, CPU, or GPU. And then we create a queue associated to that device, and then we'll pass that queue as the first parameter to the functions. And then another change is creating the data parallel C++ one-dimensional buffer from, in the example we're showing from host data, but you can also initialize it on the GPU itself. And so just to keep it more consistent with the C example we showed. And then you can see the function call. It had been, cblaz dgem. Now it is MKL namespace. And then within the MKL namespace are different namespaces for the domains. So GEMM is part of blaz, so it's in the blaz namespace. And then GEMM, we drop the character specifying the precision and do overloading based on the data types. And then, as we said before, you take the queue as the first parameter, and then we also have oneMKL defined enum types for the transpose operations, similarly for side, upload, and so forth. And then you can also see that instead of passing the A, B, and C arrays, you now pass A buff, B buff, and C buff, the buffers, hence the buffer-based API. And now if we want to change it again and look at the unified shared memory or pointer-based API, there's new changes now shown in green. So here, the USM data parallel C++ APIs return an event to specify when the computation is done. So we need to capture that event. We use malloc shared to allocate the pointer so it can be accessible from the host and from the device, and you pass the device you want and the context taken from the queue as parameters as well. And then there's optional input not shown, where you can pass a vector of events that you want to wait on before the computation happens. So in case any of your matrices, say, are coming from previous calculations, so you need to wait on those calculations to finish before you can compute the matrix multiplication. And then the synchronization is handled by the user with the unified shared memory APIs. And so, for example, if you wanted to print the matrix, you can wait on the event that is passed from it, the GEMM done, until that finishes, and then you can, then you'll know the computation is finished, and you can use the output C matrix as you wish. So those are examples of our the data parallel C++ APIs, and now we can look at the OpenMP offload example. So starting again from our C API, we just have a few changes here to enable the OpenMP offload, shown in blue. So first we have a specific header file that you include to enable the OpenMP offload to occur, MKL OMP offload.h. Then you have a couple of pragmas that you need. So you have a target data map, which pragma, to send the matrices to the device. So you're saying you want to map A and B to the device and the C matrix to and from it. And you can pass in the the number of the device that you want to use. If you don't, it'll use the default 0. And then within that pragma, you have a target variant dispatch. So you're saying you have a variant of the functionality that you want to run. And so this notifies that the computations on the GPU is requested. Yes, there's a question, but can you go to a microphone if you don't mind?
Are these standard OpenMP structs, or are they in the standard?
They're currently extensions for, but they may be supported in the future where we prefer standardization.
Yeah, thank you.
So then use the target variant dispatch to notify that the GPU computation is requested. And then you list all the device memory pointers in the use device pointer clause. And this is, and if it happens that it's not able to offload, the device isn't found, this is still valid code that would run on the host. So the computation would still be able to proceed, but just not offloading. But you'd still get the results. So if you're interested in checking out, it's available in beta form. As I said, we had the initial beta release in November and an update earlier this week, and then we'll have some more updates going forward. You can participate on our forum, use the link line advisor tool, which has been updated. And then one other thing I want to point out is the oneMKL specification. So as we mentioned before, oneAPI is based on industry standards and open APIs. And so that extends to the different libraries in there. And so we really want to have community involvement in driving the oneMKL specification that then is ideally useful for the community. So if you'd be interested in being part of defining the oneMKL specification or other specifications that are part of oneAPI, let me know. That'd be great. You can go to oneapi.com to check it out. And that's it. Thank you.